It started as a dot, not a planet, not a face, not a message, just a single point of light sitting where nothing should have been. An astronomer stared at the screen for a long time before saying anything. Then, months later, when the team pointed the same instrument at the same patch of sky again, hoping to confirm what they'd found, it was gone. This is the real story of what the James Webb Space Telescope actually found when it turned its eye toward our nearest stellar neighbor, and why the truth is stranger and in some ways more unsettling than the headline you clicked on. Because here is the first thing you need to understand. Webb did not see Proxima Centauri for the first time. Astronomers have been staring at that star for over a century. What Webb did was something much harder, much stranger, and much more revealing, and it tried to see what's hiding around it. And what it found, and then lost, and then found evidence of again, is one of the tensest ongoing mysteries in modern astronomy. Stay with me. Because by the end of this, you'll understand why some scientists are calling this the most technically extreme observation ever attempted, and why the star at the center of it all might be far more dangerous than anyone wants to admit. Proxima Centauri sits just over 4 light-years from Earth. In cosmic terms, that is next door. It is the closest star to our Sun, a small, dim, reddish ember of a star, a red dwarf, cooler and fainter than the Sun, invisible to the naked eye from most of Earth's northern hemisphere. It's part of a larger triple-star system called Alpha Centauri, alongside 2 brighter, sun-like companions, Alpha Centauri A and Alpha Centauri B. For decades, Proxima Centauri was just a footnote, a nearby star interesting mostly for its proximity. Then, in 2016, ground-based telescopes using a technique called radial velocity detected something extraordinary, a small wobble in the star's light, a rhythmic tug caused by an unseen object pulling on it gravitationally. A planet. Roughly Earth-sized, orbiting close to its dim star, but close enough to the right distance that liquid water could theoretically survive on its surface. They named it Proxima B. The scale of what that meant took a while to sink in. The nearest star to our Sun, a rocky planet, in the habitable zone, not 100 light-years away, not 1,000. 4. Since then, astronomers found 2 more worlds in the same system, Proxima C, a colder planet farther out, and Proxima D, a small world discovered more recently, orbiting so close to the star that a year there lasts only days. 3 planets, 1 star, right next door. And every single one of them was found the same way, indirectly, through gravity, through the tiny mathematical fingerprint a planet leaves on its star's light, detected by instruments on the ground, in Chile, using spectrographs sensitive enough to measure a stellar wobble smaller than walking speed. Nobody had ever actually seen one of them. Not a pixel, not a smudge, just numbers, and the confidence that numbers like that don't lie. Radial velocity works because a planet doesn't just orbit its star, it tugs back. Gravity runs both ways. As Proxima B circles its star, the star itself wobbles ever so slightly in response, and that wobble stretches and compresses the wavelength of the star's light in a rhythm that repeats with mathematical precision. Instruments on the ground, in the high, dry mountains of Chile, are sensitive enough to measure that stretch down to a matter of centimeters per second, slower than a person walking. It is an extraordinary technique. It is also fundamentally indirect. It tells you a planet is there. It tells you roughly how big it might be and how far it orbits. It does not tell you what the planet looks like. It does not tell you what's in its atmosphere, if it has one at all. For that, astronomers need something radial velocity can never provide, light that comes directly from the planet itself or passes through it, rather than light borrowed secondhand from the wobble of a star. That's where Webb comes in. The James Webb Space Telescope, launched in December 2021, is not a planet-hunting machine by design. Its primary mission, the reason it was built, was to look at the most distant galaxies in the universe, light that has been traveling for over 13 billion years, from the edge of observable time itself. Pointing a machine like that at a star 4 light-years away sounds almost absurdly easy by comparison. It is not. Here's the problem, and it's a problem that sounds simple until you actually think about the numbers. A star like Proxima Centauri, even a dim one, is unimaginably brighter than any planet orbiting it. We're not talking about a difference you could compensate for with a longer exposure. We're talking about a brightness ratio in the range of hundreds of thousands, sometimes millions, to 1. Imagine trying to photograph a firefly hovering a few inches from a lighthouse beam from miles away while the lighthouse is still running at full power. Now imagine the firefly isn't even confirmed to exist yet. You're trying to catch a glimpse of something you only know about because of a mathematical wobble measured years earlier by a completely different instrument. That is roughly what Webb was attempting when astronomers turned its mid-infrared instrument, MIRI, toward the Alpha Centauri system. MIRI is one of Webb's 4 science instruments, and it's built to detect longer infrared wavelengths. Heat, essentially, radiating from cool, faint objects. It's the same instrument that has photographed newborn stars wrapped in dust and traced the glowing structure of distant galaxies. But turning it toward a target this close, this bright, this fast moving across the sky required something Webb had never really been asked to do before. Astronomers had to build an entirely custom observing sequence. They used a technique called coronography, essentially placing a small mask inside the instrument to block the overwhelming light of the star itself, the same way you might block the sun with your thumb to look at something near it in the sky. Except in this case, the sun is moving, the telescope is moving, and the target, if it exists at all, might be barely brighter than the noise left behind by the masking process itself. The team pointed Webb first at Alpha Centauri A, the brighter sun-like member of the triple system, rather than Proxima itself. And in 2025, after years of preparation, they found something, a source of light. Faint, consistent with a gas giant planet, orbiting at roughly twice the distance Earth orbits our sun. Meaning, if it's real, it sits inside or near the system's habitable zone. Researchers described it as the most significant exoplanet imaging result Webb had produced to date. If confirmed, it would be the closest planet ever directly imaged around a star that closely resembles our own sun in age and temperature, and one of the closest habitable zone worlds ever detected, at a system just 4 light-years from Earth. For a moment, it felt like confirmation, a picture, actual light bouncing off or radiating from an actual planet. Then they looked again, and the second time, the planet wasn't there. Not a fainter version of it, not a shifted position consistent with orbital motion, nothing. The signal that had been present in the earlier data simply did not reappear in follow-up observations. For a team that had spent years designing a custom sequence just to catch a glimpse of this thing, that absence was almost worse than never finding it at all. Here's where the story could have gone 2 very different directions. It could have quietly died. An interesting blip, dismissed as noise, forgotten in a technical appendix nobody outside the field ever reads. Instead, the researchers did something rarer and frankly more honest. They ran the numbers again. They modeled the planet's likely orbit based on the original detection, and they asked a simple question. Is there a plausible orbital position where this planet could have been during the second observation that would have placed it too close to the glare of its star to be seen at all? The answer was yes. Computer simulations suggested the candidate planet may simply have swung, in its orbit, into a position too near Alpha Centauri A's blinding light for Webb's coronagraph to separate it from the star. Not gone, just hidden, temporarily, behind the very glare the entire observing technique was designed to work around. It's an elegant explanation. It's also, notably, unconfirmed, which means right now there is a candidate planet orbiting the nearest sun-like star to Earth that has been photographed exactly once, tentatively, and never seen again, sitting in a kind of scientific limbo, real enough to publish, uncertain enough that nobody is willing to call it confirmed. One astronomer involved in reviewing the findings described the situation carefully. Any claim this significant, especially one built on a single image of an object this faint, needs independent confirmation before it can be trusted. The signal, they noted, sits right at the edge of what current image processing techniques can reliably extract from Webb's data. That is scientific caution talking. But sit with the plain version of it for a second. The most advanced space telescope ever built pointed itself at our nearest stellar neighbor, captured what looked like direct evidence of another world, and then, on the second look, saw nothing. There is a strange cultural echo buried in this particular candidate planet, too. If the gas giant orbiting Alpha Centauri A is eventually confirmed, it would orbit at a distance eerily similar to the fictional setup imagined decades earlier in a well-known science fiction film franchise, a massive planet in roughly the right zone around one of the 2 sun-like stars in this exact system, with room for smaller, rockier worlds to exist in its shadow. Fiction got there first, imagining the geography before astronomers had the tools to test it. Now the tools exist. They just haven't finished the job. Now here's where the story turns toward Proxima Centauri itself, because Alpha Centauri A was only half of the target list. While the Alpha Centauri A search played out in public, with press conferences and published papers, a separate and quieter effort was underway, aimed specifically at the dim red star next door, Proxima Centauri. Unlike its brighter neighbor, Proxima wasn't just a candidate hunt. Proxima already has 3 confirmed planets. The question wasn't whether something was there. The question was whether Webb, of all instruments, could actually see one of them directly. Specifically, whether it might be able to detect the faint heat signature of Proxima b, the rocky Earth-sized world sitting in the star's habitable zone. A study published in the journal Icarus took this question seriously enough to build an entire simulated observation from scratch. Researchers modeled what Webb's MIRI instrument, using its coronagraph, would actually see if it stared directly at Proxima Centauri, hunting for a planet roughly Earth size, orbiting at a distance where liquid water could theoretically exist. They didn't just imagine a clean, empty background. They built noise into the simulation deliberately, dust drifting through the inner solar system, faint heat radiating from Webb's own structure, tiny distortions in the optics themselves. All the invisible interference that stands between a real observation and a clean result. Then they tested whether a simulated Earth-sized planet, tucked into that noisy, realistic scene, would actually be detectable. The distances involved are almost absurdly small by astronomical standards. Researchers modeled planets sitting somewhere between roughly a fifth and half of an astronomical unit from Proxima Centauri, meaning, in real terms, closer to their star than Earth is to our Sun, but around a dim red dwarf, where close is exactly where you'd expect liquid water to survive. At that range, a planet would complete an entire orbit, an entire year, in a matter of months. The simulation pushed Webb's capabilities to their absolute limit, and that phrase, the limit, keeps appearing throughout this entire story, over and over, in paper after paper, not beyond the limit, not safely within range. The limit. The exact edge of what the most powerful space telescope in human history can currently pull out of the dark. Why does any of this matter? Why should the fact that scientists are testing detection limits on a computer feel like anything more than a technical footnote? Because of what's actually sitting there, because of what kind of star Proxima Centauri really is. Here's the part of the story that earns the word terrifying, and it has nothing to do with faces in the data or hidden signals. It has to do with the star itself. Proxima Centauri is what astronomers call a flare star. Small, cool, red dwarf stars like it are common throughout the galaxy. In fact, they're the most common type of star there is. But their size comes with a violent temperament. Because they're so compact, their magnetic fields tangle and snap with tremendous energy relative to their size, unleashing flares, sudden, intense bursts of radiation, far more frequently and proportionally far more powerfully than a calm, stable star like our Sun. In 2019, astronomers caught Proxima Centauri in the middle of one of the largest stellar flares ever recorded from any red dwarf. In the span of a few seconds, the star's brightness in far ultraviolet light spiked by a factor of roughly 14,000 times brighter. In seconds. To put that in perspective, our own Sun does produce flares, occasionally powerful ones, capable of disrupting satellites and power grids here on Earth, but even the Sun's most extreme recorded flares don't come close to that kind of proportional spike. Proxima Centauri isn't an unstable outlier either. This is simply what red dwarf stars do. They are the most common stars in the galaxy, quietly outnumbering Sun-like stars many times over, and a huge fraction of them are locked in the same violent pattern, calm for hours or days, then a sudden blinding pulse of high-energy radiation, then calm again. That single detail reshapes an entire branch of the search for life beyond Earth. For years, the excitement around red dwarf systems came from a simple piece of orbital math. Because these stars are so dim, their habitable zones sit much closer in, which makes the resulting planets easier to detect using the wobble technique that found Proxima b in the first place. Small stars, tight orbits, detectable signals. It seemed for a while like an efficient shortcut to finding habitable worlds in bulk. The flare problem is the shortcut's hidden cost. A planet sitting close enough to a red dwarf to enjoy liquid water temperatures is, by definition, sitting close enough to take the full, undiluted force of every one of those flares, over and over, for billions of years. If Earth orbited a star that behaved like that, a flare of that scale wouldn't just disrupt a satellite or two. It would be an extinction-level event for anything living on the surface unprotected. A wave of radiation capable of stripping away atmosphere, sterilizing exposed biology, and doing it again and again, because Proxima Centauri doesn't produce flares like this once. It produces them regularly as a fundamental part of how the star behaves. And Proxima b, the rocky Earth-sized planet sitting in the star's so-called habitable zone, the same planet Webb's simulated observations were designed to hunt for, orbits close enough to that star that habitable zone and danger zone may functionally be the same place. This is the tension driving the entire modern hunt around this system. Proxima b sits at exactly the right distance for liquid water, and it orbits exactly the kind of star that might make surviving there, for anything delicate enough to call life, close to impossible. Some researchers have proposed that a planet like Proxima b could still hold on to an atmosphere if it has a strong enough magnetic field of its own, shielding it the way Earth's magnetic field protects us from solar wind. Earth's magnetic field is generated by the churn of molten iron deep in our planet's core, and it deflects the bulk of incoming solar particles around us rather than through us. If Proxima b generates a similarly strong field, an atmosphere could, in theory, survive even repeated battering from its star. Others argue that a young, active red dwarf like Proxima Centauri would have blasted away any early atmosphere long before the planet had a chance to develop one, leaving nothing behind but bare, irradiated rock. Red dwarfs like Proxima Centauri are thought to have been even more volatile in their youth, spending their first several hundred million years in an unusually active phase, throwing off flares and high-energy particles at a rate far above what we observe today. A young rocky planet caught in that bombardment before it had time to build a stable magnetic shield or a thick enough atmosphere could have lost its most volatile gases into space permanently, stripped away, molecule by molecule, before life ever had a chance to begin. Nobody knows which version is true, not yet. That's precisely why Webb's observations matter so much, and why the difficulty of making them matters even more. If astronomers can eventually detect an atmosphere, or the absence of one, around Proxima b, it would be one of the most consequential answers in the history of the search for life beyond Earth. Not proof of life, but proof of whether the conditions for it can even survive that close to a star this violent. That is the real stakes behind the technical language, the coronagraphs, the simulated noise models, the custom observing sequences. Somewhere in that data, hidden behind a wall of stellar glare 14,000 times brighter than baseline in a single flare, might be the answer to whether the nearest habitable zone planet to Earth is actually habitable at all, or whether it's been sterilized over and over by the very star that gives it its warmth. Now here is where the story needs to slow down, because this is exactly the point where speculation tends to run ahead of what's actually been shown. Nothing about the Icarus simulation study confirms that Proxima b has an atmosphere or that it doesn't. It's a feasibility study, a rigorous, carefully modeled test of whether Webb's instruments are even capable, in principle, of pulling a signal that faint out of that much noise. The researchers weren't announcing a discovery. They were asking whether a discovery is possible at all and under exactly what conditions. Likewise, the Alpha Centauri A candidate planet, the one seen once and then not seen again, remains formally unconfirmed. It has not been verified by an independent team. It has not reappeared in a way that would remove reasonable doubt. The astronomers who found it have been explicit that this kind of signal, sitting at the outer edge of what image processing techniques can currently deliver, requires exactly the kind of skepticism the scientific process is built to enforce. This is worth dwelling on, because it's easy for outside observers to hear unconfirmed and assume the scientists involved are simply being cautious for caution's sake. That's not quite it. The history of exoplanet imaging is full of promising signals that later turned out to be instrumental artifacts, background objects that happen to line up in just the wrong way, or subtle flaws in how starlight blocking data gets processed. A single detection, however exciting, is a hypothesis. Two independent detections, ideally using different instruments or techniques, start to look like a discovery. That threshold exists precisely because the alternative, announcing new worlds that later evaporate under scrutiny, erodes the credibility the entire field depends on. And Proxima Centauri's flare activity, dramatic as it is, doesn't automatically mean Proxima b is lifeless. Extremophile life on Earth survives in environments once thought completely uninhabitable, deep-sea vents, acidic pools, the underside of Antarctic ice. Whether something similar could persist under a red dwarf's radiation, particularly if the planet has a strong magnetic field or a thick enough atmosphere to absorb the worst of each flare, is a genuinely open scientific question, not a settled one. The honest version of this story isn't Webb saw a terrifying secret and scientists are hiding it. The honest version is stranger, in its own way, than that. It's a story about a machine built to look at the edge of the observable universe being pointed, instead, at the closest possible target, and discovering that close doesn't mean easy. It means fighting through a wall of stellar light bright enough to erase a planet from the data entirely, aiming for a target so faint that a single stray photon of noise could be mistaken for a world, or a world could be mistaken for nothing at all. Consider the strangeness of that for a moment. Webb has photographed galaxies whose light left home before the Earth's continents had settled into their current shapes, distances so vast they're almost meaningless to a human mind. And yet turning that same telescope toward our next-door neighbor, 4 light-years away, close enough that a chemical rocket could theoretically reach it within a few generations, required more customized engineering, more painstaking analysis, more caution about false signals than almost anything else Webb has attempted. The universe, it turns out, doesn't get easier to see just because it gets closer. Sometimes it gets harder, because the thing blocking your view isn't distance. It's glare. It's a star sitting right in front of the thing you're actually trying to see, refusing to get out of the way.